Modular origami or unit origami is a paper folding technique which uses two or more sheets of paper to create a larger and more complex structure than would not be possible using single-piece origami techniques. Each individual sheet of paper is folded into a module, or unit, and then modules are assembled into an integrated flat shape or three-dimensional structure by inserting flaps into pockets created by the folding process. These insertions create tension or friction that holds the model together. Definition and restrictions. Modular origami can be classified as a subset of multi-piece origami, since the rule of restriction to one sheet of paper is abandoned. However, all the other rules of origami still apply, so the use of glue, thread, or any other fastening that is not a part of the sheet of paper is not generally acceptable in modular origami. The additional restrictions that distinguish modular origami from other forms of multi-piece origami are using many identical copies of any folded unit, and linking them together in a symmetrical or repeating fashion to complete the model. There is a common misconception that treats all multi-piece origami as modular, but this is not the case. More than one type of module can still be used. Typically, this means using separate linking units hidden from sight to hold parts of the construction together. Any other usage is generally frowned upon. History. The first historical evidence for a modular origami design comes from a Japanese book by Hayato Ooka published in 1734 called Ranmazushiki. It contains a print that shows a group of traditional origami models, one of which is a modular cube. The cube is pictured twice and is identified in the accompanying text as a Tamati Buko, or a magic treasure chest. Isao Honda's World of Origami appears to have the same model, where it is called the cubical box. The 6 modules required for this design were developed from the traditional Japanese paperfold commonly known as the menko. Each module forms one face of the finished cube. There are several other traditional Japanese modular origami designs, including balls of folded paper flowers known as kasudamas, or medicine balls. These designs are not integrated and are commonly strung together with thread. The term kosudama is sometimes, rather inaccurately, used to describe any three-dimensional modular origami structure resembling a ball. There are also a few modular designs in the Chinese paper folding tradition, notably the pagoda and the lotus made from just paper. Most traditional designs are however single-piece, and the possibilities inherent in the modular origami idea were not explored further until the 1960s, when the technique was reinvented by Robert Neal in the USA and later by Mitsunobu Sonobe in Japan. The 1970s saw a sudden period of interest and development in modular origami as its own distinct field, leading to its present status in origami folding. One notable figure is Steve Krimble, who discovered the potential in Sonobe's cube unit and demonstrated it could be used to make alternative polyhedral shapes, including a 30-piece ball which remains popular to this day. Since then, the modular origami technique has been popularized and developed extensively, and now there have been thousands of designs developed in this repertoire. Types. Modular origami forms may be flat or three-dimensional. Flat forms are usually polygons, stars, rotors, and rings. Three-dimensional forms tend to be regular polyhedra or tessellations of simple polyhedra. Modular origami techniques can be used to create lidded boxes which are not only beautiful but also useful as containers for gifts. Many examples of such boxes are shown in Fabulous Origami Boxes by Tomoko Fuse. There are some modular origami that are approximations of fractals, such as Menger's sponge. Macromodular origami is a form of modular origami in which finished assemblies are themselves used as the building blocks to create larger, integrated structures. Such structures are described in Tomoko Fuse's book Unit Origami Multidimensional Transformations. Notable modular paper folders: Robert Neal, Mitsunobu Sonobe, Tomoko Fuse, Kunihiko Kasahara. Francis Au, Tom Hull, Meenakshi Mukherjee, Heinz Strobel, Miyuki Kawamura, Rona Gerkwitz, Bennett Arnstein, Valerie Van, David Mitchell, Christina Birchik, Twirligami, Steve Crimble, Modeling Systems. Robert Neal's penultimate module. Robert Neal developed a system to model equilateral polyhedra based on a module with variable vertex angles. Each module has 2 pockets and 2 tabs on opposite sides. The angle of each tab can be changed independently of the other tab. Each pocket can receive tabs of any angle. The most common angles form polygonal faces: 60 degrees, 90 degrees, 108 degrees, 120 degrees. Each module joins others at the vertices of a polyhedron to form a polygonal face. The tabs form angles on opposite sides of an edge. For example, a subassembly of 3 triangle corners forms a triangle, the most stable configuration. As the internal angle increases for squares, pentagons and so forth, the stability decreases. Many polyhedra call for unner-like adjacent polygons. For example, a pyramid has 1 square face and 4 triangular faces. This requires hybrid modules, or modules having different angles. A pyramid consists of 8 modules, 4 modules as square triangle, and 4 as triangle. Further polygonal faces are possible by altering the angle at each corner. The Neal modules can form any equilateral polyhedron, including those having rhombic faces, like the rhombic dodecahedron. Mukhopadhyay module. The Mukhopadhyay module can form any equilateral polyhedron. Each unit has a middle crease that forms an edge, and triangular wings that form adjacent stellated faces. For example, a cube octahedral assembly has 24 units, since the cube octahedron has 24 edges. Additionally, bipyramids are possible, by folding the central crease on each module outwards or convexly instead of inwards or concavely as for the icosahedron and other stellated polyhedra. The Mukhopadhyay module works best when glued together, especially for polyhedra having larger numbers of sides. Bibliography. Tomoko Fuse. Unit Origami. Multidimensional Transformations. Japan Publications. ISBN 0-87040-852-6. Tomoko Fuse. Fabulous Origami Boxes. Japan Publications Trading. ISBN 0-870409786.